All right, welcome everybody. So let's go over our lecture from today. So we started out here with talking about chemical equations. And so in our chemical equations, we have reactants and we have products. And so let's look at just an example here for fun, making a s'more. And so our reactants in our s'mores is we usually have 2 graham crackers, right? One for the bottom, one for the top. Let's say we're going to use 1 marshmallow and we're going to take 3 chocolate squares. And so when we put all that together, we have our product, which is a s'more. And so it's important to remember here with our chemical equations, we want our reactants and our products to be balanced. So we want the same amount on each side. And so we can see that here with our s'mores example. We started with 2 graham crackers. Well, we still have those 2 graham crackers. We started with 1 marshmallow. That marshmallow is still there. We had 1, 2, 3 squares of chocolate. It's a little tough to see, but we still have 1, 2, 3 squares of chocolate. So our equation here would be balanced because we have the same amount that we started with and the same amount at the end. So now let's get a little bit deeper here. Let's think about alpha decay. And so we've talked about 3 different types, alpha, beta, and gamma. Let's first focus on alpha decay. So when an alpha particle is released, or you can think subtracted, a few things are going to happen. So let's first think about our alpha particle. So He for helium, mass number of 4, and atomic number of 2 there. And so what this is telling us is when we release this alpha particle, what we started with, that mass number is going to be reduced by 4. And our atomic number is going to be reduced by 2. And so as we go through and we look at these example equations, we definitely want to make sure and double check that our masses and our atomic numbers on both sides of the arrow are equal. And so that means that they're balanced. So let's go ahead and let's take a look at our first equation down at the bottom here. So we can see here that we are going to be starting with radium-226. And so remember, this is our mass number right here. And this right here would be our atomic number. And so what radium-226 is about to do is it's about to undergo alpha decay. And so we can see our alpha particle there. And so when this alpha particle is released, we can see that our mass number here, 226, we are taking away 4. And so our new mass number that we're going to have over here is 222. Now we can see the same thing happen to our atomic number. So we started with an atomic number of 88. And then our atomic number was reduced by 2 here. So we take 88 minus 2, and that's going to give us a new atomic number of 86. And so if we wanted to figure out what element this is, we go to the periodic table. We would look and see which element has an atomic number of 86, and we would see here that it is Rn for radon. And so like I said, it's important to make sure that it is all balanced at the end, right? So let's start with our mass number here. So I started with, on the left side of our equation, a mass number of 226. So let's see if that equals what's on the right side here. So we're going to add our 4 with our 222, and that equals 226. So perfect. That is balanced. Now let's look at our atomic number. So we started with an atomic number of 88. So let's see here. Does 2 plus 86 equal 88? Well, yes, it sure does. So everything is balanced there. All right, so now let's go ahead and let's take a look at beta decay. And so in beta decay, a beta particle is released, or you could think subtracted. And so what's going to happen here is when this beta particle is released, our mass number does not change. But our atomic number is going to be increased by 1. And so what our beta particles are is it's a neutron that breaks down into an electron and a proton. And we can see that up here. We have our neutron, and here it's breaking apart into our proton and our electron. So what happens is our proton here is going to stay in the nucleus, but our electron is going to leave. So it's going to be emitted. And so what that does is it makes the atom more stable. So let's look at our example equation down here now. So we have calcium 47. And so calcium 47, that isotope is about to undergo beta decay. And we can see that here by seeing our beta particle. So we just learned that our mass number is not going to change when beta decay occurs. And so we can see that here, our mass number is 47, and then it stays 47 over here. Now, though, what's going to happen is our atomic number is going to be increased by 1. So this was our starting atomic number, 20. And then we're going to increase it by 1. So our new atomic number should be 21. And so now we can go ahead, double check, is everything balanced? So we'll start with our mass number. So our mass number, we started with 47. And let's see, does 0 plus 47 equal 47? Yep, that's balanced. All right, so now let's look at our atomic number. So our starting atomic number was 20. And now on the right side of our equation, we have a -1 plus 21. Or you could write that as 21 minus 1. Either way is fine. But that's still going to get us 20. So perfect. That matches. Everything here is balanced. All right, we're going to look at one more type of decay here. Our last one is gamma decay. So in gamma decay, a gamma ray is released. And we learned the other day that our gamma rays have no mass and they have no charge. And so because of that, when something undergoes gamma decay, our mass number does not change and our atomic number does not change. And it's still important to double check. Make sure that our masses and atomic numbers on both sides are equal, that they are balanced. So we have our example equation down here. So we have GD, that stands for gadolinium. So we have gadolinium 148, and it's about to undergo gamma decay. Remember, that's our symbol for gamma. And so our mass number doesn't change, and we can see that here. We have 148 and 148. And again, our atomic number should not change. We have 64 and 64. So everything is balanced here. All right, so now we're going to go through some examples. So we're going to take a look and think about which type of nuclear radiation is present below. So we're going to look at our equation at the bottom. Well, to figure out what type of radiation is occurring, we want to look at what particle is present in the equation. And we can see right here, we have our alpha particle. So that means alpha decay is going to be occurring. Now our second question here, we just want to see if it's balanced. So let's go ahead and do a little bit math. So we'll focus on, I'll do it in a different color here. Let's see, I'll go green. All right, so we're going to look at our reactants and we're going to look at our products. So to figure out if it's balanced, let's start with our mass number. So our number up on top. So to the left side of our arrow, we started with 226. Now on our right side, we have 4 plus 222, and that equals 226. So perfect. That's balanced there. Now let's double check our atomic number. So we started with 88. Now we're going to go ahead. We'll look on our right side here. So 2 plus 86. Well, perfect. That equals 88. So our equation is balanced. All right, let's look at another example here. So which type of nuclear radiation is happening here? Well, we're going to start out looking for our particle. And we can see here that we have a beta particle. So beta radiation is occurring. Now, is it balanced? Well, let's start with looking at, again, I'm going to switch my colors. We are going to look at our reactants and our products. So for our mass number, we started with 47. And then to the right side of our arrow, we have 0 plus 47. That equals 47, so perfect. Now let's take a look at our atomic number. We started with 20. And on this side, we have -1 and 21. Or you could think about it as 21 minus 1. Either way is fine. That still gets us 20. So perfect. Yes, everything is balanced. All right. Our next example here. What type of nuclear radiation is present? Well, we look for a particle, and we can see our gamma symbol. So gamma radiation here, gamma decay is occurring. Now let's double check to see if things are balanced. This one we can visually see. We have 148 on the left, 148 on the right. So that's good. 64 on the left, 64 on the right. Everything is balanced. All right, now let's do some practice on solving for the missing reactant. So what we need to do here is we need to figure out what should go here. What we do know is whatever goes in that spot, we can see that it's going to undergo beta decay. And so remember, with beta decay, our mass number stays the same. And our atomic number is going to increase by 1. So, since we know our mass number is going to stay the same, we can look at the mass number of our products here, 40 plus 0, that's 40. There we go. And then now we can figure out what our atomic number would be. So what we can do is we know that whatever the atomic number is going to be right here, it was increased by 1. So over here we have 20. So what we can do is we can go 20 minus 1. And so that gives us 19. You can also do it by just taking our -1 plus 20, and that gives us an atomic number of 19. So when I look at my periodic table, I see that potassium has an atomic number of 19. So now I can go back, put my K for potassium. And I should always double check to make sure that everything is balanced. So for my mass number here, I started with 40. And then on the right side, I have 0 plus 40. That equals 40. Perfect. That's balanced. My atomic number. On the left, I have 19. And then I have -1 plus 20, which also equals 19. So perfect. Everything is balanced. All right. So now we're going to go ahead and solve for a missing product. So this time we're going to figure out what should go on this end. So I have my reactants of what I'm starting with, and we can see that it's going to undergo beta decay here. So if we remember, our mass number is going to stay the same. So I can carry this 35 over here. And then if we remember, our atomic number is going to increase by 1. So I can just take 14 plus 1, and that equals 15. All right. So before I go and find the element, I'm going to take a moment and just double check that my numbers are balanced. So my mass number, I had 35 on the left side of the arrow, and then I have 0 plus 35 on the right, which also equals 35, so perfect. Now let's check my atomic number. I have 14 on the left. On the right, I have -1 plus 15, or you can think 15 minus 1. Either way, that gets you 14, and that matches up. Oh, yes, there we go. All right, so let's go to my periodic table and look for my element now that has the atomic number of 15. So I look and I see I have phosphorus here, atomic number of 15. So I come back and I can put a P for phosphorus. All right, just a few more examples here. So now our job is to fill in all of these spots. And so we have our scenario here. We have the alpha decay of radon 198. So we have a few important pieces of information in that short little sentence. The first one, alpha decay. So that means I need to put in my alpha particle. So I'm going to go ahead and do my HE, 4 and 2. My second important piece of information is from radon 198. And so remember, this is an isotope name. So I have my name of the element, and then remember, this is our mass number. So our symbol here for radon is Rn. Our mass number is 198. So what I can do is I can just go ahead, come to my periodic table, look for radon here, and I see it has an atomic number of 86. Perfect. There we go. So now I can go ahead and finish this alpha decay. So remember with alpha decay, our mass number here is decreased by 4. So my starting mass number is 198. So I go ahead and I subtract 4 and I get 194. So that is my new mass number. And then my atomic number is decreased by 2. So I started with 86 and I minus 2, and that gives me a new atomic number of 84. So I'll write that in. Let's just quickly double check and make sure my numbers are balanced. So with my mass number here, started with 198. And then on the right side, I have 4 plus 194. Sure enough, that equals 198. Mass number is balanced. Let's double check the atomic number. I started with 86. So 2 plus 84, that equals 86, and perfect. Those are balanced. So now let's go to the periodic table and see which element has an atomic number of 84. And I can see it's polonium there, PO. And there we have it, our alpha decay of radon 198. All right, now let's do a beta decay of uranium 237. So again, a few important pieces of information. The first one, it's going to undergo beta decay. So I can put my beta particle. That's done. Now I have my isotope name, uranium-237. So my element symbol is U for uranium, and my mass number there is 237. So I can go to the periodic table and see what is my atomic number for uranium. And I can see it is 92. So I come on back, go ahead, and I put that right there. Now we can undergo our beta decay. So remember, at beta decay, our mass number stays the same. So I bring 237 over here. And now remember, our atomic number is increased by 1. So I just take 92 plus 1, 93. Let's just double check, make sure everything is balanced. So my mass number here started with 237. And then on the right side, I have 0 plus 237. That equals 237. Perfect, that's balanced. Now my atomic number started with 92 on the left, and I have minus 1 plus 93, or you can think 93 minus 1. Either way, I get 92, and perfect. So that is all balanced. So now I can go to the periodic table, see what element has an atomic number of 93, and that would be neptunium here, NP. So I come back, and there we go. And that was all for our lecture today.